Hello everybody, welcome back to our channel. In this video we're going to be solving a PHY7B momentum practice problem. As usual, if you're finding this content helpful, please make sure to leave a like and subscribe to our channel. So the problem statement is the following. Please feel free to pause the video in order to copy the problem so that you can actually follow along. So in this problem we basically have 4 different scenarios in which we have some cards and some masses and some velocities, initial and final. And the question is basically, for each scenario, decide whether the total momentum of the 2 cards is conserved in the horizontal direction. Explain why or why not. So as you can see, I have the first 2 scenarios here copied on my notebook, and I also have the other ones on a separate piece of paper, so I'll just change as we move along. Now, for this particular problem, you absolutely do not need 100% a momentum chart, but the reason why I decided to go with this quiz is because I think this is fantastic if you want to get some, practice doing your momentum charts and also just figuring out or learning how to figure out if momentum is conserved or not. So definitely you absolutely do not need a momentum chart. It is not necessary. You could just use equations, but it is very helpful and it is very visual, and if you do a momentum chart, then you just know things are gonna be right. So the first scenario is a moving card sticks to a stationary card and they bounce off a wall, and we're given the masses and we're given the velocities, initial and final. So now let's just fill in our momentum chart for this scenario. So momentum is equal to mass times velocity, and we do have, we don't have actual numbers, but we can very easily just figure out the momentum in terms of m and b. So for this car, which is the one that's on the left, we do have an initial momentum because we have a mass and a velocity, so we're just going to go mb, going in this direction. Now for car 2, we do not have an initial momentum because obviously the car has a mass, but it is not actually moving, so it does not have an initial momentum. Now the total just has to add up in the column, so the total is just going to be MB right here. Now of course, what we're trying to figure out is if there's going to be anything over here, because this is your delta P total of your system. So if this is 0, then momentum is conserved. If this is not 0, then that means that no, momentum was not conserved in this scenario. So we're basically building up to figuring out if we're going to have anything here. So now the final. So for the final, I'm basically going to multiply. The new velocity for both of these is b divided by 3. So b final is just b initial divided by 3. And then the masses are just m and m. So if I multiply m times b third, that's just going to be b divided by 3 over here, and it's just going to go to the left. Now this mass over here, for the second car, let me just go back for a second. Oh, okay, so this is 2m on the problem. Yeah, so this is 2m on the problem. Yeah, I've done this problem so many times in office hours, I already know the answers. So this is actually 2m per the instructions. I just did a little mistake copying the problem. So now we just have to multiply 2m times b divided by 3, and that's just going to be 2/3 mb. So it's just going to be a little bit of a bigger arrow over here. And then this has to add up like this. So if I add everything up, I'm just going to get 1/3 plus 2/3 that is going to be equal to 3/3. So that is going to be just 1 mb going on this direction. Now, we already have everything that we need to figure out whether momentum is conserved, because on a momentum chart, the rows have to actually add up. So I just need to figure out what goes in here. Obviously, this is not going to be 0. So let's just figure out what the actual number is. Let's just go with another color, I guess. So we have MB, and then what goes here in order to have MB on the other direction? The answer is just 2 MB, like bigger arrow, so 2 MB. So we do have something in here, and because we do have something in here, this automatically means that momentum is not conserved. There we go. So momentum is not conserved in this scenario. Final answer. Very easy to see if you actually do a momentum chart, because you know exactly where you're looking for. There is no doubt in your mind. They are very visual. You know, it would be very easy if you're just going with equations, and this happened on this quiz a lot, to just be like, oh, initial is MB, final is MB, it was totally conserved. But no, because as you can see on the momentum chart, momentum is a vector, and because momentum is a vector and direction matters, because we flipped our direction, then no, momentum was actually not conserved in this scenario. So feel free to, just fill in these two spaces, just use vectors of abstraction. It's going to be very good practice actually, but I'm just going to go ahead and move to the second scenario. So in the second scenario, the problem statement reads, a ball is dropped into a moving cart. So you basically have a little ball that's flying over here going down, and then you have a car that's going to the right, and then basically just the ball drops and then everything is moving together. So let's just see if momentum is conserved. For this momentum chart, I'm only gonna look at the horizontal axis, which is just the x-axis, because the problem itself told me very specifically that they only cared about the x-axis. So even though this little guy, the ball, is moving on the y component, it doesn't really have any initial velocity on the x component, and for that reason, its initial momentum is gonna be 0. So now moving on, the car does have some initial momentum on the x-axis because it has a mass and it has a velocity. So it does have an initial momentum of 4 mb. Just moving in this direction. And then these have to add up. So this is 4 mb. Again, this is what we're looking for. If there's something here, then momentum is not conserved. If this is 0, then yes, it was conserved. So we're holding on to this. So now the final scenario is both of the objects are moving, and they are moving at the exact same velocity. So we just need to multiply mass times velocity for the ball, mass times velocity for the car, and that's gonna be it. So for the ball just has a mass of m. So m times this velocity is just gonna be 4/5. Oh, that's 4/5 mb, like this. So it's just going to be something like this, right? And then for the ball, we need to multiply 4m times 4/5 of b, and that is going to be equal to 4 times 4 divided by 5. So 16. Let's just leave it as 16/5 mb. There we go. So this is obviously just going to be like another arrow going on this direction. Now we have to actually add the fractions, so 4/5 plus 16/5, because they have to add up going down. So we have 20/5, and that is 20. Yeah, so 20/5 is equal to 4, so we have 4 mb, and there we go. Oh my goodness, the scale of this is just not okay, but we're just looking at these values over here, so let's just concentrate on the actual numbers and not the scale, because obviously the scale is not gonna add up at this point. But it doesn't really matter. What matters here is that in order to fill this in, we need to ask ourselves 4 plus what is equal to 4, and the answer to that is 0. So because we do have a 0 over here, we found out that delta P total is equal to 0, then in this scenario, momentum is conserved. Final answer. So see, this is basically the exercise. Just start with your momentum chart, and then you just figure out here and here, and then if this is a 0, momentum is conserved. If this is not 0, momentum is not conserved. So let's just move on to the next scenario. I have it over here. There I go. So this is scenario number 3, and the problem statement reads as follows. 2 carts that are initially attached by a spring and moving together get separated. So they're moving together at a velocity b, and then they basically get separated So let's see what happens over here. So one of the cards, this one over here, has a mass of 3m. So its total momentum is just gonna be multiply that. So it's just gonna be 3mv. So just put an arrow over here. The other one is just mass m, velocity v. So it's just gonna be a third of that. And if we add this up, we're gonna end up with 4mv over here, like this. Now this is what we want to figure out, but we do have the final situation, so let's see. So this is mass m, this is the one 3m, like this. So let's see. So this one over here, the first card, the one that's 3m, is now moving at twice the velocity, so 2v. So we just need to multiply that and we get 6mv. You know, 2v times 3m, I'm sorry, that's just going to be 6mv, like this. Now for the other one that's moving on the other direction, we have 2v times m, so that is going to be equal to 2vm, or 2mv, it's really the same thing. And if we add them up, we just need to be careful because these two are actually going on different directions. So if we add this vector and this vector, we're gonna get 4. Oh, I'm sorry, we're gonna get it. Okay, so as I was saying, this is gonna be a total of 4mv in this direction. And again, now remember that we're looking at this part over here. So when you think about it, 4 plus what is equal to 4? Well, that would be 4 plus 0. And because this number is a 0, then momentum is conserved. And there we go. So now for the final scenario, we have, let me just read the problem real fast. So is two moving cards stick and continue to move together. So both of them are initially moving at different velocities, but then they basically get stuck together. So let's see, let's just follow, you know, what we've been doing so far. So we have one of the cards has mass m, velocity 2v. So if I multiply that, I'm gonna get 2mv going in this direction. The other card has a mass of 2m, but a velocity of only 1b. So if I multiply that, I will also get 2mv. And if I add all of this, 2 plus 2 is just going to be equal to 4mv, like this. So now for the final, they are both moving together at a velocity of only 1b. So if I just do my multiplication, so mb, that's just going to be 1mv in this direction. And 2m times b, it's going to be 2mb in this direction. So if I add this up, then I'm going to get 3mb moving to the right. So now in order to figure this out, remember it's 4 plus what is equal to 3. Well, that would be -1 going in this direction. And because this is not 0, then immediately you can just say that momentum is not conserved. Now again, for these scenarios, you didn't necessarily, I mean, it just wasn't a requirement that you do 4 separate momentum charts. However, it is just so useful when you do it this way. And you actually get to know as a fact that you got the problem right, because visually speaking, it is very easy to distinguish your left, your right. It's a visual tool. I don't know, I just like it a lot. And this is how I solved the problem when it was first given to me. So anyways, I hope that this problem was helpful for you guys. Again, if you're finding this helpful, a like is very much appreciated. So I'll see you guys in the next video. Bye.